Hey, what's up, guys? Welcome to my algebra geometry lecture. So previously, I think I proved the following: is that if you haven't seen my previous video, that you can check it. So, given a commutative ring, one can define a so-called let's call it n. This is called the neo-radicals. So basically, it's all the element in the ring such that there is a integer, positive integer, such that x to n is 0. And we have shown that the spec A, so the spectrum of A as a topological space is homeomorphic to the spec A quotient. And so basically the reason is that this neo-radical is all the prime ideals intersection. So that your spectrum of as your affine skin as a topological space cannot detect the nilpotent. So this is why some people say that skin is a generalization of variety. One fact that in a skin that you can add a nilpotent. Okay, so this is why in the future that we need to add the structure sheaf. Okay, so in this video, I'm just gonna prove this fact that the connection between the affine skin and this irreducibilities. So I want to say that if let's say X is spec A is irreducible, so this is the theorem. If and only if A quotient n is integral domain. And obviously that obviously that this is the same as this n is what is prime ideal. Because prime ideals n is a prime ideal if and only if A quotient n is integral domain. Okay. So this proof is basically using the fact that so let's prove this. Okay, so let's say one is these directions. Okay, so let's prove. Okay, so let's say okay, maybe it's 2. Okay, so let's assume that so we prove these directions. Basically, we want to say that maybe let's prove. Let's prove this. So first, let's assume that x is reducible. Okay, and we want to show that if x is reducible, then A quotient n is not the integral domain. Okay, so this is our goal. Not the integral domain. Okay, so one obvious way is that since we already proved this spectral A is homeomorphic to A quotient n, so we can just assume that n is 0. Okay, so this is very simple. We assume n is 0, and we want to prove that A is not integral domain. Okay, so proof is very simple since x is reducible. So we can write x into y1 union y2, where y1, y2 are proper. And close. Okay, so and I can take I of x. So recall that I of x is all the intersection of prime ideals belongs to x. So I of x, by definition, this guy will be a neo-radicals. And by definition, I say this guy is 0. So I get this. Okay. Okay. So y1 and y2 are proper subset. Okay. So this tell you that if I of y1 is non-zero and I of y2 is non-zero, then obviously what? Obviously that okay, let me just so this is the statement that I want to say. If I of y1 is non-zero and I of y2 is non-zero, then what? Let's say you take the element of f belongs to y1, and you take element g belongs to iy2. This tells you that f times g will belongs to iy1 intersection iy2. The reason is that I of y1 is the intersection of prime ideals in y1, I of y2 is the intersection of prime ideals in y2. So their products will be in I of x, right? Either intersection, which is 0. Okay, but for the problem is that let's say I of y1 is non-zero, so I can choose f to be non-zero. I of y2 is non-zero, so I can choose g to be non-zero. But the fact is that f times g must be in the intersection, and intersection must be 0 by our definition. So fg will be 0. Okay, so f non-zero and g non-zero. This shows that A is not integral domain. Okay, so you might ask that why I of y1 is not 0. Okay, very simple, because I say I of y1 are proper closed subset, right? So I of y1 will be all the prime ideals p in y1. Okay. Okay. So which tell you that since x is reducible, right? So your I of y1 will not be x, right? Because I of y1 will be just the subset of x, right? So their intersection cannot be all I of x. Okay. Because y1 is a proper subset. Okay. So which tell you that I of y1 is not 0 and I of y2 is not 0, because I say y1 and y2 are proper subsets. Right? If I of y1 is the same as x, then this is contradiction for y1 and y2 are proper close. Okay, conversely. So conversely, we want to say that A is not a domain. And we want to tell you that we want to say that X is reducible. Okay, so this direction we need to we need to say that if you have A is not domain, right, then you can find F non-zero, G is non-zero, and such that Fg is non-zero. And we want to use this fact and split X into 2 parts. Okay, so this is very simple, right? Because we need to separate X into 2 parts. Okay, so very simple is that if f is non-zero, so I can consider the singleton of f, the vanishing set of f, which is the prime ideals. F do not belong to that prime ideal, and sorry, f belongs to that prime ideal. Okay, and then you can consider v of g, where is a prime ideal such that g belongs to that prime ideal. Okay, so f is non-zero, right? So f is non-zero. This tells you that the v of the singleton cannot be x. Okay, the reason is f is non-zero, right? So f is non-zero. So v of the singleton will be the radical of f, where if you take all the prime ideals belong to v of singleton f. This is the property of these radical ideals. So if you take this, right, then this guy is the same reason. The same reason, right? This guy f is non-zero cannot be x. Okay, so let's suppose you prove by contradiction, right? You say this guy is x. Let's say this guy, v of singleton f is x, then this guy will be all the prime ideals of v of x, and will be the neo-radicals. Then by my assumption, then I say neo-radical is 0, so you get 0. Right? But if the radical of f is 0, that means that f is 0. Right? Because if the radical, this is a set, right? The set of f ideal generated by f is 0, that means f is 0, but I say f is non-zero, right? So this is contradiction. Okay. So this means that if f is non-zero, then v of singleton cannot be x. Okay. The same reason, the v of singleton of g will not be x. Okay. So this tell you what? This tell you that if you write your vf singleton intersection with v singleton of g will be what? Will be vanishing set property will be singleton of fg. But f of g is 0, so you get v of 0. Then the vanishing set, all the prime ideal contains x. Contains 0, so this guy is x. Okay, so this tells you that this x can be split into two closed subsets, which is proper. So these are closed. This is by Zariski topology, by definition, right? V of f is closed. And f is non-zero, so tell you that these are proper. So proper subset, proper subset. So you can write x split into two proper subset, so which proves that x is reducible. Okay, so this is the proof of this theorem. Yeah, so this gives you just tell you that the irreducibility of the affine schemes if and only if the A quotient important is integral domain. Okay, so this is the property that that also commonly used. Okay, so see you guys next videos.